This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
I'm going to get P is equal to P naught and U is equal to 0. So that defines region 1 everywhere until this first characteristic, everywhere inside here, can be reached either from a characteristic that's negative or positive, and it'll be of this form. So in region 1, P is equal to P naught and U is equal to naught. But now, let's go back a little bit. So this C minus characteristic that starts here, it goes back here, intercepts the piston at the point 1. So now you have to update what's going on at 1, and you're going to work out what the constant is on this characteristic, C1 plus. And if I worked out what was the nature of this characteristic, then I could intercept this characteristic by the negative one from here at, say, some point 2, or, point 1 would be the same as a point up here. They would be exactly the same because it's reached by a characteristic from here, and it would have a positive characteristic from here, and so there might be some intersection, say, with one from here at some point here. And so this point here would be the same as this point 2. So let's work out what happens at 2. And then we'll know what happens in the whole of the region 2. Do you understand?
Could you explain what characteristic is again, please?
Yes, it's a particular curve along which P and U behave in a particular way. Namely, that on the characteristic, P minus P naught minus rho naught A naught U on a C minus characteristic is a constant. And so we have to work out what the constant is. But it's because I worked it out in one particular case of just a wave going to the right. We know that for a wave going to the right, the pressure doesn't change as I move along the wave. So if I move to the same point on the wave, so if I move a distance x, which is equal to A naught t, I see there exactly the same thing as I had at t equals naught and x equals naught. So that's the whole idea. And I don't want to belabor it, but it's a very powerful idea. The method of characteristics is a very powerful idea. So,
just one more question, please.
Yeah.
On the x-axis there, you've got some scribble 1, 2, 3.
Psi 1, psi 2, psi 3, they're just the values of x that intercept the characteristic. So the C minus characteristic would be, for example, psi minus A naught t. Because if I integrate dx dt is equal to minus A naught, I have to have a constant, right? And so it's the constant when t equals naught. So this is the characteristic that goes through this point, and this is the characteristic C plus. Dx dt is equal to plus A naught that goes through at t equals naught. It's here at psi 2. So these are psi 1, psi 2, psi 3. They're just any point that I choose in the tube at time t equals naught. And there are two characteristic curves from that point. One of them is dx dt is equal to plus A naught, and the other one is dx dt is equal to minus A naught.
So does that physically reflect a wave traveling in 2 directions?
It could, but the characteristic, it would be the curve along which something doesn't change. Something doesn't change. So whatever it is at some point, we'll find out. So we can propagate. And so it's a wonderful idea. So I've said here, so in region 1, everywhere in this region here on this XT diagram, I can reach every point here from a C minus characteristic and a C plus, and it's no surprise to you that everywhere the pressure is P naught and the velocity is naught. What is surprising is what happens when this characteristic meets the piston, because we know that the piston has a velocity and it ain't zero. So I should be able to work out the constant here. I should be able to, on this characteristic, I should be able to work out what the pressure is as a result of the velocity here. And then I know that it's the same everywhere along there, the same constant. All right, so now how does that work? So on all C minus beginning at t equals naught, P minus P naught minus rho naught A naught U is equal to 0, and all C plus beginning on t at t equals naught on that axis, P minus P naught plus rho naught A naught U is a constant. So in region 1, where these two characteristics would intersect, you can see that if I add the two, I get 0 on the right-hand side, and therefore I have 2P minus P naught is equal to 0, so P is equal to P naught. So in region 1, P is equal to P naught, and therefore U must be 0 to satisfy these two relationships. However, the reflection of a C minus from the piston, so on that C1 minus, P minus P naught minus rho naught A naught U is equal to naught. But at the point 1, right here on the piston, P1 minus P naught will be minus rho naught A naught U, whatever the velocity of the piston is. So it's UP. So on the C1 plus that goes through 1, P1 minus P naught plus rho naught A naught U, and U is equal to UP at the piston, will be a constant. So I can work out what that constant is. And P1 minus P naught will be rho naught A naught UP. So the constant will be 2 rho naught A naught UP. So the constant is 2 rho naught A naught UP. So now we can see what would happen if I took this point 2. So here's my point 2, and I have the intersection of the characteristic from here and the characteristic on C1 plus. So what happens at point 2? So at point 2, the intersection of the C2 minus and the C1 plus, the C2 minus is P2 minus P naught minus rho naught A naught U is equal to 0. And so at the point 2, P2 minus P naught minus rho naught A naught U2 is equal to 0. And on the C2 plus, or C1 plus, I mean, I'd have P minus P naught plus rho naught A naught U is the constant, is 2 rho naught A naught UP. So now you can see that I have two equations here for two unknowns, P2 and U2. So if I add them, I get P2 minus P naught is this thing here. So P2 minus P naught is a half of that, which is rho naught A naught UP. And since since P2 minus P0 is rho naught A naught UP, it means that U2 is equal, from this equation or from this one either, U2 is equal to UP. So that's terribly significant here, because it's saying that in the whole of region 2, everywhere, P is a little higher than the ambient pressure, and the velocity is to the right. U is equal to UP to the right. So that will be true because I've worked it out for this particular point. This particular point would be the same as this point, would be the same as any point in this diamond here. So in that whole region 2, the pressure is slightly higher than the ambient pressure, and the velocity is not zero. So we've got a propagating wave to the right in that region, and then it's being reflected from this closed end. So now what happens when we reflect it? So we've worked out what goes on in region 2. And now at the closed end, on the positive C1 plus characteristic, in general, everywhere on that characteristic, P minus P naught plus rho naught A naught U is equal to the constant, which was 2 rho naught A naught UP. But at 3, we're given the velocity. Namely, that I've got an end wall there, and that's a boundary condition on the velocity, that U is equal to 0. I'm going to do the open flute in a minute, where that boundary condition is on the pressure and not on the velocity. Makes a big difference. But at 3, U3 is equal to 0. So U3 is equal to 0, so I can put that into there, and it says that P3 minus P naught is 2 rho naught A naught UP. So you notice that the compression that I had is reflected as a compression. It's even higher. The pressure is even higher now, as we'll see. So P3 minus P naught is that. So on a minus, P minus P naught minus rho naught A U is equal to a constant. So what's the constant? Well, the constant is at 3. I can work this on C3 out. P is equal to P3. And U is equal to 0 at 3. So the constant is P3 minus P naught here, which I just worked out as 2 rho naught A naught UP. So the pressure now at 3 is higher than it was in region 2. So on C3 minus, the minus characteristic going through that point, P minus P naught minus rho naught A naught U is now this constant 2 rho naught A naught UP. And so now I could work out what happens at 4. It's a constant, and I can evaluate it at points at which I know, where I know something. So I can evaluate it at the piston, where I know the velocity, I don't know the pressure, and I can evaluate the constant at the closed end, where I know the velocity and I don't know the pressure. When I do the open end, I'll evaluate it when I know the pressure, but I don't know the velocity. So So 4, how would I find what goes on here at 4? I'd take a C plus characteristic from region 2, it'd be the same as the C1 plus characteristic. And I'd take the C minus characteristic from 3 and I'd intercept them at 4. So what happens? So at 4, on the C1 plus, I had, at 4 on the C plus, P4 minus P0 plus rho naught A naught U was the constant, 2 rho naught A naught UP. And on C3 minus, P, which is this one here, P4 minus P0 minus rho naught A naught U4 will be 2 that. So if I subtract one from the other, I get that U4 is, if I subtract this, I get 2 rho naught A naught U4, and 1 minus the other is 0 here, so U4 has got to be equal to 0, and if U4 is equal to 0, then P4 minus P0 is 2 rho naught A naught UP. So what has happened is, as a result of this closed end, I have the compression being reflected as another compression. The pressure is a little bit higher. It's 2 rho naught A. So there's a discontinuity in pressure, goes up, but the velocity goes to 0. So you can build up a picture as to what might happen. So now let me look at reflection from an open end, and this was a great surprise to me when I first saw it, when I first thought about it and worked it out for myself. So what happens at 3? Well, on the C1 plus, that'll be the same as in the other problem. P minus P0 plus rho naught A naught U is 2 rho naught A naught UP. We worked that out before from this intersection here of this velocity with the piston. Oh yeah, that's right. This is supposed to be the vertical line here, and here's the path of the piston. So at 3, what do I know? I know, and this is a bit of an approximation, at that open end, I'm going to say that the flow is subsonic and the pressure is going to be the same as the ambient pressure. So P will be P0. I don't know what the velocity would be, but the pressure will be the ambient pressure because the flow's coming out. It's like Helmholtz's classical problem for the organ pipe, where he assumed Helmholtz was very clever, and he assumed that the pressure was unchanging out there. And that's the Kelvin-Helmholtz instability is basically because he worked on organ pipes. So the pressure is known at 3, and it's equal to P0. So that says that U3 here is going to be 2 UP, twice the velocity of the piston. That comes as a surprise. How could I have twice the velocity of the piston at that open end? But I do, according to this. And so I'm going to show you how it works. So on C3 minus, P minus P0 minus rho naught A naught U is a constant. And at 3, the constant then will be P3 is equal to P0, and the constant is going to be minus 2 because here the constant then is P is equal to P0, and so the constant is this thing here, but U3 is 2 UP, so it's minus 2 rho naught A naught UP. That's the constant on the C minus. So you can see something interesting. So on the C3 minus that goes through that point, P minus P0 minus rho naught A naught U is minus 2 rho naught A naught UP.
Sorry to interrupt. I missed the end of last lecture.
Oh, because that is a consequence of the form of the equations. The form of the equations said that you could integrate them, dp plus rho a du, and then you could just integrate them, p minus p naught plus rho naught a naught u was a constant. And that is true for the linear case. It's not what is true for the nonlinear case. So at this point 4, which is the intersection now of a C3 minus and a C1 plus, what happens? So at 4, P minus P naught plus rho naught A naught U is 2 rho naught A naught UP, that's the C plus, and on the C minus P naught minus rho naught A naught U is minus 2 rho naught A naught UP. It follows that if I add the two equations, P4 is equal to P naught because these two add to 0 and these two add to 0. So P is equal to P naught, and therefore U is equal to 2UP. So in that region, 4, everywhere, the velocity is twice the piston's velocity. Comes as a surprise. The pressure is the atmospheric pressure, but the velocity is twice the piston's velocity. So at the open end, a compression reflects as an expansion. The pressure went up in the compression wave, and then I came to an open end and the pressure went down. So the compression that I had reflected as an expansion at the open end. That's unlike the closed end where the pressure reflected as a compression. So now, just to complete the picture to go on, it's sort of interesting. I think it's interesting. What happens at 5? Well, at 5, I don't know the pressure, but I do know the velocity. So I should be able to work out the constant at 5, and then I have a C plus going through 5, and I can take the C minus, which will be the same as the C3 minus from here, and I could find this 0.6. So what happens? Well, I don't want to belabor this. You can...
Gary?
Yes?
How is it that you get the reflection from the open end?
How is it?
Yeah.
Well, because what is prescribed at the open end is not the velocity, but the pressure. And that's not the pressure behind the wave. So you had the wave coming up to the open end, but the open end requires the pressure to be 0. And the only way to do that is to double the velocity. That's what's going on. And this is really like the reason for resonance in this pipe. If you have an open end, you get half wavelength resonance. Okay. So at 5, on the C3 minus, we've worked that out. On a C3 minus, we have P minus P naught minus rho naught A naught U is equal to minus 2 rho naught UP, rho naught A naught UP. So at 5, I've prescribed the velocity, but not the pressure. So P5 will be, this is amazing. This is amazing. The pressure actually goes below the ambient pressure. And that's because the velocity is U5. I think that's wrong. Oh, yes. U5 has got to be equal to, I'm prescribing at 5, the velocity has to be that of the piston. But I don't know what the pressure is, so if it's minus rho naught A naught UP, the right-hand side, then if I take it to the right-hand side, I get minus rho naught A naught UP, and so the pressure at 5 actually is below ambient pressure P naught. Yes?
Can we apply this method if the speed is supersonic?
It'll be complicated. It'll be a little subtle. It's a little subtle. Now, in the characteristics case, in the real compressible gas dynamics case, the dx dt is U plus A. But A is not constant. A depends on the temperature. And if the flow were isentropic and the temperature goes down, the speed of sound goes down. And so I'm going to tell you about that in a minute. I don't have time to actually work it out for you. Otherwise I would. I could work it out in a heartbeat. I can show you, but I don't have time to do it. But I wanted to do this much so you get some idea of what the method of characteristics is about. And this is what it's about. There are special curves along which something changes in a very simple way. On this characteristic curve, dP is rho A naught du, or dP is minus rho naught A naught du. So I can integrate it. So at this point 6, where I have a positive characteristic, P6 minus P naught will be rho naught A naught U6, and U6 is equal to UP. Oh, sorry. No. 6 was away from the piston. U5 was equal to UP. And P6 minus P naught minus rho naught A naught U6 is minus 2 rho naught UP. And so what you find is that U6 is equal to UP, and P6 minus P naught is minus rho naught A naught UP. So an expansion reflects as an expansion from the solid surface of the piston. All right. So how does this all work? I said that the piston velocity, here's the piston velocity, it's constant and it's UP. But the gas has zero velocity up to the length L initially in region 1. The gas has zero velocity. But then in region 2, it had twice UP. So there's a region where the velocity is twice UP. And that extends until the characteristic comes back again, which is about 3 L over A naught, if you assume that the velocity of the piston is negligible compared with the speed of sound. And then if you go on, you'll find that it's 2 UP. There's zero velocity here, and then it's this velocity here. And wait a minute. I think, how do I want to move this figure to the right. I'm pretty sure I did something to the right of that figure. No, it's all right. It's all right. No, it's all right. It's all right. I'll come back to it in a minute. I come back to it in another figure in a minute. So now, what is the linearized shock tube? So you will have heard about shock tubes, and I'm going to tell you what a real shock tube looks like in a minute. But I'm going to begin by showing you what is a linearized shock tube. And that's a simple case where I have a driven gas here on the right where P is equal to P naught and there's zero velocity initially. And I have a slightly higher pressure on the other side, and this is a balloon. So all we're talking about is a burst balloon, a one-dimensional burst balloon. What happens in a one-dimensional burst balloon? And if you want to think about a real shock tube, you want to think about Hiroshima, where you have a massive explosion, And, well, instead of rupturing a balloon, you're rupturing the equivalent of a very large diaphragm. And I'll talk to you about it, what happens in a very, very large high-pressure shock tube. But I want to do the linearized case. So here's the linearized shock tube. So this is just a diaphragm here. And this pressure is P naught plus delta P, and here's the diaphragm, and then this is zero pressure here. All right, so now what happens? Well, it's an easy case because this diaphragm can be thought of as like a rupturing diaphragm here, and that it will be the equivalent of my piston moving suddenly to the right. And I'll send a wave forward and a wave back. And I want you to see what I send forward and what I send back. I'm going to send an expansion back, and I'm going to send a compression forward. Okay, so let's work it out. So I have my C1 plus characteristic, P minus P naught plus rho naught A naught U is equal to 0 here. And on this one here, P minus P naught minus rho naught A naught U is equal to 0 because right here, P is equal to P naught and U is equal to naught. But what about at 2? 2, I have a slightly different constant. So, I just told you what happened in this region 1 here. P minus P naught plus rho naught A naught U is 0, and P minus P naught minus rho naught A naught U is 0. So in region 1, everywhere in here, P is equal to P naught and U is equal to 0. Nothing at this time here. I know something about the fact that I ruptured a balloon here, but I don't down here. It doesn't get to me until I get the signal from the acoustic wave, A naught. So, but what about from this point here? Let's take the C2 plus and the C2 minus. Well, they're easy to work out because I know that the velocity is 0 initially, but the pressure is not 0. So on C2 plus, P minus P naught plus rho naught A naught U is delta P, because U is 0 and P minus P naught is delta P. And on the C2 minus, P minus P naught minus rho naught A naught U is also delta P. And so everywhere in region 3, P is equal to P naught plus delta P, and U is equal to 0. Well, we knew that. But what about in region 2? Well, on the C2 plus, I have P minus P naught plus rho naught A naught U is delta P. And on the C1 minus, which came from the region at rest in region 1, I have P minus P naught minus rho naught A naught U is equal to 0. So it follows, if I add the two, 2P minus P naught to P2 minus P naught will be delta P, or P2 minus P naught will be a half delta P. So I have the compression going to the right and the expansion going to the left, and the pressure drop across the expansion is a half delta P, and the pressure drop across the compression, the pressure increase across the compression is a half delta P. And you can see that if I subtract the 2, add 2, if I subtract the 2, I get plus rho naught. Subtracting this goes out, and I get 2 rho naught A naught U is equal to delta P, or in other words, the velocity in region 2 is a half delta P over rho naught A naught. So I have a very small velocity. If I divided that by the speed of sound, U over A naught will be a half delta P over rho naught A naught squared. And rho naught A naught squared is about P. So it says that U over A naught is a very small quantity, delta P over P naught, approximately. And so that's what happens when you rupture the balloon. If I blew up the balloon and I thought of it as a one-dimensional balloon, then it's exactly what happens. I send forward a compression wave, and I send back into the balloon an expansion wave. And of course, that receives an expansion wave coming from the other side of the balloon, if it were a real balloon. But I'm doing a one-dimensional case. So here, everywhere, here's my XT diagram. Everywhere in this region here, the velocity is U is a half delta P over rho naught A naught, rho naught A naught. Everywhere in here. Everywhere in here, the velocity is to the right. Here, the velocity is not moving at all. Here, the velocity is not moving at all, but here it is everywhere moving to the right. So that's, so I made this little remark here. Acoustics doesn't distinguish expansions from compressions. Real gas dynamics does, but acoustics does not. So now another important idea that has spatial implications as well is the idea that you could cancel a wave. So you can see how we could cancel a wave. Let's work it out. So here's my piston velocity. What if I required this piston, when this wave comes back here, what if I required the piston to instantaneously stop? Suppose it instantaneously stopped. Would I cancel the wave? Well, that's a good question. We can work it out. So we have the C1 characteristic, and I have a C1 plus, and I've worked that out for you, and the C3 minus from a closed end. The C3 minus is P minus P naught minus rho naught A naught U was 2 rho naught A naught UP. And I worked that out for the closed end before. So now let's suppose that I bring this C3 minus back here to 5. But at 5, I know the velocity. I imagine the velocity was 0. And so the question is, do I cancel the wave? So at 5, since I know the velocity at 5 is 0, P5 minus P naught is 2 rho naught A naught U naught. So on C5 plus, from here, the plus 1, P minus P naught plus rho naught A naught U is a constant, but U is equal to 0, and P5 minus P naught is 2 rho naught A naught UP, so it's 2 rho naught A naught UP. So at 6 here, I have a plus characteristic from here, which I just worked out, is this constant, and the minus characteristic from 3, which intersects it, is the minus characteristic is P minus P naught minus rho naught A naught U is this. So therefore, everywhere P6 So you can see here that if I add the two, yes, if I add the two, I have 0 here. So P6 minus P0 will be 2 rho naught A naught UP. That's what the pressure is in this region here, whereas the velocity in here is 0, and that is true everywhere. So I've cancelled the wave. I've precisely cancelled the wave. U equals 6, and that's a very important idea. Can you cancel a wave? And in supersonic flows, this analogy to the time problem is also analogous to weak waves in a spatial problem. And yes, you can cancel a wave in the supersonic flow. So that's an important idea. And here you can see something interesting, and this is what I wanted to show you. So it cancels exactly if this time, when I made the piston velocity 0, is exactly the time from here to here, which is L over A naught, plus the time to come back again, which is L over A naught, so it's 2L over A naught, if the speed of the piston velocity is very tiny compared with A naught. So what is the change in volume from here? And how does that, would I expect this pressure to arise from an isentropic compression? Well, let's just see what I get. So the change in volume is the velocity of the piston times the time Tc, but the time Tc is 2L over A naught, so it's 2L over A naught UP. So the volume divided by the original volume is 2 UP over A naught divided by the original volume, which is just length. So I've just assumed the area of this tube is 1. So the original volume was the length L, so delta V over V is minus 2 UP over A naught. Well, is that what I would have expected? And the answer is most certainly yes. And can't quite see it. But I can tell you what it is. Beg your pardon?
See on the keyboard if you're going down and up, try right. Yeah, just to the right.
Yeah, there we are. Thank you. So you'll know that for an isentropic compression, PV to the gamma is a constant. So if I take logarithms and differentiate, I get delta P over P, or dP over P, plus gamma delta V over V is equal to 0 for small quantities when I differentiate. So that says that the gamma, I've worked this out. Yes. So and the delta P is rho naught A naught UP, and delta P over P is minus gamma delta V, and so I got the delta P over P here, I worked it out here, is 2 rho naught A naught UP divided by P naught, which was rho naught A naught squared over gamma, because gamma P naught is over rho naught is A naught squared. So this delta P over P gives you, when you put this in here, minus gamma delta V over V, which is exactly the same as I would have written down here. So it all makes perfect sense. I moved the piston, I changed the volume, and I changed the pressure, and then I kept it constant at a new volume, and nothing else happens. I cancelled the wave. There's no reflections anymore. I cancelled it exactly. So that's a very interesting problem to work out. So now, let me close by telling you a little bit about the nonlinear case, and I can't do it for you. But the nonlinear case, again, uses the method of characteristics, but the characteristics now have a velocity u plus a, or u minus a, and that may mean that if a is variable, the characteristics would cross. And any of you who have surfed know precisely what I mean, that the wave breaks. The wave's coming in, and why? Because the speed of the wave is the square root of gh, and that means that the top of the wave is moving higher than the bottom of the wave, and so the top goes faster than the bottom, and the wave curls over and breaks. So that's a breaking wave. An expansion, by contrast, the temperature falls, the speed of sound falls, and so the characteristics don't cross, they get further apart. And so the shock tube, which think of Hiroshima, a one-dimensional Hiroshima, where we've got extremely high pressure, and we've got an imaginary diaphragm moving to the right. What would happen? So this imaginary diaphragm, I've called, and the language for the shock tube in the shock tube community is the contact surface. It's between it's where the piston is that drives the driven gas on the one side and the driver gas on the other side. And in some cases, for example, that driver gas could be hydrogen, and the driven gas could be argon and nitrogen, or argon and helium, a whole range of possibilities. So people have looked at shock waves, very, very large shock waves. This is how people knew a lot about what was going to happen when they developed the bomb. They knew all of this. So now there are going to be 4 regions. There's the region that knows nothing about the shock wave. That's the time before it arrives. This is the time after the shock wave. And the shock wave, of course, causes a velocity to the right, a very high pressure, and a very high temperature. And that's what took the roof off the building in Hiroshima. Here's the contact surface. And behind the contact surface now, I'm moving this piston, if you like, to the right. It's going to send an expansion back. But the characteristic curves are u minus a. And since the speed of sound is falling, and u is also falling as I go further back here, then these characteristics, instead of crossing, they become like a fan and they open out. That's in the real nonlinear case. It's no longer simply minus a naught t. And so what happens is that you have, so here's the contact surface here, and you have continuity in the pressure and continuity in the velocity across the contact surface. But ahead of it, you have the very high strength shock wave ahead of it. That's what does the damage, of course, that very high strength shock, because not only is it high pressure, it's very high velocity, and it's very high temperature, very, very high temperature. And that's why the terrible things happened. So here's the plot, a one-dimensional shock tube with a very high driver pressure. I have a very high temperature behind the shock wave, ambient temperature ahead of the shock wave. There's the shock wave there. It's moving to the right. I have this high temperature, and then across the contact surface, the temperature falls because that fluid at the contact surface is conservation of pressure, but it's now moving to the right. And so it has a low temperature. And then the temperature rises because the pressure rises up to and this is the expansion fan here. P2 is equal to P3 and U2 is equal to U3 is the contact surface condition. The contact surface can be considered as a massless piston moving with a velocity U2, and the shock forms between 1 and 2 because the characteristics cross. Yes?
Why T4 is not equal to T1?
Why? Beg your pardon?
T4 is not equal to T1.
It could be, but it may not be. It depends. It depends. In the case of Hiroshima, T4 was extremely high. This is a one-dimensional bomb. So it could be, and it may not be, but if you want to get the maximum strength shock wave, you make T4 very high. T4, and you make P4 very high. But it doesn't have to be. I just drawn it arbitrarily there. But T2 is even higher across the shock, or it may be. Maybe. Depends how you see. Depends on the driven gas and the driver gas. And the driver gas may not be the same as the driven gas, and in many cases it's not. But shock tubes are the basis for a whole lot of applications with very large shock waves. So people have studied very, very high strength shock waves in shock tubes. So there's a standard shock wave in the basement. Most people use shock tubes if they have very high strength, very high large shocks. They'll be done in defense establishments because it'll be classified because of its application to weapon systems, explosives of one form or another. But in Moscow, I can tell you, I went to the sub-basement, and we went into the sub-basement, and the guy pulled on a string, and the light went on, and the place was festooned with dust. And we went to his office, and I saw on the wall a Mollier diagram for liquid metal. So what did I conclude? What would you conclude? I concluded that they were doing shape charges for penetration of armor, and they were. So if you want to go through steel, you want to try and use a shock wave that'll melt the steel. And so you use a very high strength shock. Anyway, I digress. I must quit. All right, I'll just close with this. Well, now we're going to start next week. I finished unsteady gas dynamics. Unfortunately, there's so much more that could be said. But it's a very big area, unsteady gas dynamics. And we'll do the last of compressible flows in steady supersonic flow. Oh, that's right. Tomorrow, yes. It's so there'll be probably time. I'm likely to end next Wednesday, and so there'll be a review on next Thursday of next week. So you can ask me anything you like. Well, that'd be stupid. That'd be stupid. I'm not going to tell you what's on the exam. What I can tell you is that I am very keen, as you will have gathered, that you actually understand something. I am mortified that you sit there like blotting paper and think that you can just read what I've written. That won't help. You have to understand what I'm doing. So if you don't understand it, you should be asking questions. What do I care if you ask a question? You can put your head above the parapet and it won't make any difference to me or to you